IPv6 jumbo payload. In some TCP IP networks, such as those used to interconnect supercomputers, the normal 64 kilobytes limit on the IP datagram size can lead to unwanted overhead when moving large amounts of data. The IPv6 jumbo payload options specify an IPv6 datagram with payload size larger than 65,535 bytes called a jumbogram. This option need not be implemented by nodes attached to links with MTU sizes below 64 kilobytes. The jumbo payload option provides a 32-bit field for holding the payload size for datagrams with payloads of sizes between 65,535 and 4 gigabytes. When a jumbogram is formed for transmission, its normal payload length field is set to 0. As we shall see later, the TCP protocol makes use of the payload length field in order to compute its checksum using the internet checksum algorithm described previously. When the jumbo payload option is used, TCP must be careful to use the length value from the option instead of the regular length field in the base header. Although this procedure is not difficult, larger payloads can lead to an increased chance of undetected error. Tunnel encapsulation limit. Tunneling refers to the encapsulation of one protocol in another that does not conform to traditional layering, see chapters 1 and 3. For example, IP datagrams may be encapsulated inside the payload portion of another IP datagram. Tunneling can be used to form virtual overlay networks in which one network, like Internet, acts as a well-connected link layer for another layer of IP. Tunnels can be nested in the sense that datagrams are in a tunnel may themselves be placed in a tunnel in a recursive fashion. When sending an IP datagram, a sender does not ordinarily have much control over how much tunnel levels are ultimately used for encapsulation. Using this option, however, a sender can specify this limit. A router intending to encapsulate an IPv6 datagram into a tunnel first checks for the presence and value of the tunnel encapsulation limit option. If the limit value is 0, the datagram is discarded and an ICMP v6 parameter problem message, see chapter 8, is sent to the source of the datagram, the previous tunnel entry point. If the limit is non-zero, the tunnel encapsulation is permitted, but the newly formed encapsulating IPv6 datagram must include a tunnel encapsulation limit option whose value is 1 less than the option value in the arriving datagram. In effect, the encapsulation limit acts like the IPv4 TTL or IPv6 hop limit field, but for the levels of tunnel encapsulation instead of forwarding hops. Router alert. The router alert option indicates that the datagram contains information that needs to be processed by a router. It is used for the same purpose as the IPv4 router alert option. RTA-OPTS gives the current set of values for the option. 5.3.1.5 Quick Start. The Quick Start QS option is used in conjunction with the experimental Quick Start procedure for TCP or IP specified in RFC 4782. It is applicable to both IPv4 and IPv6, but at present is suggested only for private networks and not the global internet. The option includes a value encoding the sender's desired transmission rate in bits per second, a QSTTL value, and some additional information. Routers along the path may agree that supporting the desired rate is acceptable, in which case they decrement the QSTTL and leave the rate request unchanged when forwarding the containing datagram. When they disagree, like wish to support a lower rate, they can reduce the number to an acceptable rate. Routers that do not recognize the QS option do not decrement the QS TTL. A receiver provides feedback to the sender, including the difference between the received datagram's IPv4's TTL or IPv6 hop limit field and its QS TTL, along with the resulting rate that may have been adjusted by the routers along the forward path. This information is used by the sender to determine its sending rate, which, for example, may exceed the rate TCP it would otherwise use. Comparison of the TTL values is used to ensure that every router along the path participates in the QS negotiation. If any routers are found to be decrementing the IPv4 TTL or IPv6 hop limit field and not modifying the QS TTL value, QS is not enabled. Calypso. This option is used for supporting the common architecture level, the IPv6 security option Calypso, RFC 5570 in certain private networks. It provides a method to label datagrams with a security level indicator along with some additional information. In particular, it is intended for use in multi-level secure networking environments like government, military, and banking, where the security level of all data must be indicated by some form of label. Home address. The option holds the home address of the IPv6 node sending the datagram when IPv6 mobility options are in use. Mobile app IP, see section 5.5, specifies a set of procedures for handling IP nodes that may change their point of network attachment without losing their higher level or higher layer network connections. It has a concept of node's home, which is derived from the address prefix of its typical location. When roaming away from home, the node is generally assigned a different IP address. This option allows the node to provide its normal home address in addition to its presumably temporarily assigned new address while traveling. The home address can be used by other IPv6 nodes when communicating with the mobile node. If the home address option is present, the destination options header containing it must appear after a routing header and before the fragment, authentication, and ESP's header, see Chapter 18, if any of them is also present. We discussed this option in more detail in the context of mobile IP. Routing header. The IPv6 routing header provides a mechanism for the sender of an IPv6 datagram to control, at least in part, the path the datagram takes through the network. At present, two different versions of the routing extension header have been specified, called Type 0 RH0 and Type 2 RH2, respectively. RH0 has been deprecated because of security concerns, RFC 5095, and RH2 is defined in conjunction with mobile IP. To best understand the routing header, we begin by discussing RH0 and then investigate why it has been deprecated and how it differs from RH2. RH0 specifies one or more IPv6 node to be visited as the datagram is forwarded. The header is shown in figure 5.8. The non-deprecated routing header type 0 RH0 generalizes the IPv4, loose and strict source route and record route options. It is constructed by the sender to include IPv6 node addresses that act as waypoints when the datagram is forwarded. Each address can be specified as a loose or strict address. A strict address must be reached by a single IPv6 hop, whereas a loose address may contain one or more other hops in between. The IPv6 destination IP address field in the base header is modified to contain the next waypoint address as the datagram is forwarded. The IPv6 routing header, shown in figure 5.8, generalizes the loose source and record route options from IPv4. It also supports the possibility of routing on identifiers other than IPv6 addresses, although this feature is not standardized and is not discussed further here. For standardized routing on IPv6 addresses, RH0 allows the sender to specify a vector of IPv6 addresses for nodes to be visited. The header contains an 8-bit routing type identifier and an 8-bit segments left field. The type identifier for IPv6 addresses is 0 for RH0 and 2 for RH2. The segments left field indicates how many route segments remain to be processed, that is, the number of explicitly listed intermediate nodes still to be visited before reaching the final destination. The block of addresses starts with the 32-bit address field set by the sender to 0 and ignored by receivers. The addresses are non-multicast IPv6 addresses to be visited as the datagram is forwarded. A routing header is not processed until it reaches the node whose address is contained in the destination IP address field of the IPv6 header. At this time, the segment left field is used to determine the next hop address from the address vector, and this address is swapped with the destination IP address field in the IPv6 header. Thus, as the datagram is forwarded, the segment's left field grows smaller and the list of addresses in the header reflects the node addresses that forward the datagram. The forwarding procedure is better understood with an example. In Figure 5.9, using an IPv6 routing header RH0, the sender S is able to direct the datagram through intermediate nodes R and R. The other nodes traversed are determined by the normal IPv6 routing. Note that the destination address in the IPv6 header is updated at each hop specified in a routing header. In Figure 5.9, we can see how the routing header is processed by intermediate nodes. The sender S constructs the datagram with destination address R and a routing address type 0 containing the address R2, R3, and D. The final destination of the datagram is the last address in the list, D. The segment's left field, labeled left in Figure 5.9, starts at 3. The datagram is forwarded toward R1 automatically by S and R0. Because R0 address is not present in the datagram, no modifications of the routing header or addresses are performed by R0. Upon reaching R1, the destination address from the base header is swapped with the first address listed in the routing header, and the segment's left field is decremented. As the datagram is forwarded, the process of swapping the destination address with the next address from the address list in the routing headers repeats until the last destination listed in the routing header is reached. We can change to include a routing header with a simple command line option to the ping6 command in Windows XP, Windows Vista, and later include only the ping command which incorporates IPv6 support. ping6-r-s 2001:db8:100 space 2001:db8:1. This command arranges to use the source address 2001:db8:100 when sending a ping request to 2001:db8:1. The -r option arranges for a routing header RH0 to be included. We can see the outgoing request using Wireshark. See Figure 5.10. The ping request appears as an ICMP v6 echo request in Wireshark. The IPv6 header includes a next header field indicating that the packet contains a type 0 routing header followed by an ICMP v6 header. The number of segments in the RH0 left to be processed is 1. 2001:db8:100. The ping message appears as an IPv6 echo request packet. See Chapter 8. By following the next header field values, we can see that the base header is followed by a routing header. In the routing header, we can see that the type is 0, indicating an RH0, and there is one segment hop left to process. The hop is specified by the first slot in the address list, number 0, 2001 DB8 100. As mentioned previously, RH0 has been deprecated by RFC 5095 because of a security concern that allows RH0 to be used to increase the effectiveness of DOS attacks. The problem is that RH0 allows the same address to be specified in multiple locations within the routing header. This can lead to traffic being forwarded many times between two or more hosts or routers along a particular path. The potential high traffic loads that can be created along particular paths in the network can cause disruption to other traffic flows competing for bandwidth across the same path. Consequently, RH0 has been deprecated and only RH2 remain as the sole routing header supported by IPv6. RH2 is equivalent to RH0 except it has room for only a single address and uses a different value in the routing type field. Fragment header. The fragment header is used by an IPv6 source when sending a datagram larger than the path MTU of the datagram's intended destination. Path MTU and how it is determined are discussed in more detail in Chapter 13, but 1 to 80 bytes is a network-wide link layer minimum MTU for IPv6. See Section 5 of RFC 2460. In IPv4, any host or router can fragment a datagram if it's too large for the MTU on the next hop, and fields within the second 32-bit word of the IPv4 header indicate the fragmentation information. In IPv6, only the sender of the datagram is permitted to perform fragmentation, and in such cases, a fragment header is added. The fragment header includes the same information as is found in the IPv4 header, but the identification field is 32 bits instead of the 16 that are used for IPv4. The larger field provides the ability for more fragmented packets to be outstanding in the network simultaneously. The fragment header uses the format shown in Figure 5.11. In Figure 5.11, the IPv6 fragment header contains a 32-bit identification field, twice as large as the identification field in IPv4. The M-bit field indicates whether the fragment is the last of an original datagram. As with IPv4, the fragment offset field gives the offset of the payload into the original datagram in 8-byte units. Referring to Figure 5.11, the reserve field and 2-bit rest field are both 0 and ignored by receivers. The fragment offset field indicates where the data that follows the fragment header is located, as a positive offset in 8-byte units relative to the fragmentable part. See the next paragraph of the original IPv6 datagram. The M-bit field, if set to 1, indicates that more fragments are contained in the datagram. A value of 0 indicates that the fragment contains the last bytes of the original datagram. The datagram serving as input to the fragmentation process is called the original packet and consists of two parts, the unfragmentable part and the fragmentable part. The unfragmentable part includes the IPv6 header and any included extension headers required to be processed by intermediate nodes to the destination, like all headers up to and including the routing header, otherwise the hop-by-hop option extension header if only it is present. The fragmentable part constitutes the remainder of the datagram, like destination options header, upper layers header, and payload data. When the original packet is fragmented, multiple fragment packets are produced, each of which contains a copy of the unfragmentable part of the original packet, but for which each IPv6 header has the payload length field altered to reflect the size of the fragment packet it describes. Following the unfragmentable part Each new fragment packet contains a fragment header with an appropriately assigned fragment offset field. Like the first fragment contains offset 0 and copy of the original packet's identification field. The last fragment has its M, more fragments, and a bit field set to 0. The following example illustrates the way an IPv6 source might fragment a datagram. In the example shown in figure 5.12, a payload of 3960 bytes is fragmented such that no fragment's total packet size exceeds 1500 bytes, a typical MTU for Ethernet, yet the fragment data sizes still are arranged to be multiples of 8 bytes. In figure 5.12, an example of IPv6 fragmentation where a 3960 byte payload is split into 3 fragment packets of size 1448 bytes or less. Each fragment contains a fragment header with the identical identification field. All but the last fragment have the more fragment field M set to 1. The offset is given in 8 byte units. The last fragment, for example, contains data beginning at offset 362 times 8 equal to 2896 bytes from the beginning of the original packet's data. The scheme is similar to fragmentation in IPv4. In figure 5.12, we see how the large original packet has been transformed into 3 similar packets, each containing a fragment header. The IPv6 header's payload length field is modified to reflect the size of the data newly formed fragment header. The fragment header in each fragment contains a common identification field, and the sender ensures that no distinct original packets are assigned the same field value within the expected lifetime of a datagram on the network. The offset field in the fragment header is given in 8 byte units, so fragmentation is performed at 8 byte boundaries, which is why the first and second fragments contain 1448 data bytes instead of 1452. Thus, all but the last fragment possibly is a multiple of 8 bytes. The receiver must ensure that all fragments of an original datagram have been received before performing reassembly. The reassembly procedure aggregates the fragments forming the original datagram. As with fragmentation in an IPv4, see Chapter 10, the fragments may arrive out of order at the receiver, but are reassembled in order to form datagrams that is given to other protocols for processing. We can see the construction of an IPv6 fragment using this command on Windows 7. Here, in C disk C, you would put this in command prompt ping-l 3952 ff01::2. Figure 5.13 shows the Wireshark output of the activity on the network as it runs. Figure 5.13, the ping program generates ICMPv6 packets. See Chapter 8 containing 3960 IPv6 payload bands in this example. These packets are fragmented to produce 3 packet fragments, each of which is small enough to fit in the Ethernet MTU size of 1500 bytes. In Figure 5.13, we see the fragments constituting 4 ICMPv6 echo request messages sent to the IPv6 multicast address FF01::2. Each request requires fragmentation because -L 3952 option indicates that 3952 data bytes are to be carried in the data area of each ICMPv6 message, leading to an IPv6 payload length of 3960 bytes due to 8 byte ICMPv6 header. The IPv6 source address is link local. To determine the target's link layer multicast address, a mapping procedure specific to IPv6 is performed described in Chapter 9. The ICMPv6 echo request generated by the ping program spans several fragments which Wireshark resembles to display once it has processed all the constituent fragments. Figure 5.14 shows the second fragment in more detail. So in figure 5.14, the second fragment of an ICMPv6 echo request contains 1448 IPv6 payload bytes, including the 8-byte fragment header. The presence of the fragment header indicates that the overall datagram was fragmented at the source, and the offset field of 181 indicates that this fragment contains data starting at byte offset 1448. The more fragments bit field being set indicates that other fragments are needed to reassemble the datagram. All fragments from the same original datagram contain the same identification field, 2 in this case. Firewall or walls and network address translation. Introduction. During the early years of the Internet and its protocols, most network designers and developers were from universities or other entities engaged in research. These researchers were generally friendly and cooperative, and the Internet system was not especially resilient to attack. But not many people were interested in attacking it either. By the late 1980s and especially the early to mid 1990s, the Internet had gained the interest of the mass population and ultimately people interested in compromising its security. Successful attacks became a commonplace and many problems were caused by bugs or unplanned protocol operation in the software implementations of Internet hosts. Because some sites had a large number of end systems with various versions of operating system software, it became very difficult for system administrators to ensure that all the various bugs in these end systems had been fixed. Furthermore, for obsolete systems, this task was all but impossible. Fixing the problem would have required a way to control the internet traffic to which the end hosts were exposed. Today, this is provided by a firewall, a type of router that restricts the type of traffic it forwards. As firewalls were being deployed to protect enterprises, another problem was becoming important. The number of available IPv4 address was diminishing, with the threat of exhaustion. Something would have to be done with the way addresses were allocated and used. One of the most important mechanisms developed to deal with this, aside from IPv6, is called network address translation, or NAT. With NAT, internet addresses need not be globally unique, and as a consequence, they can be reused in different parts of the internet called address realms. Allowing the same addresses to be reused in multiple realms greatly eases the problem of the address exhaustion. As we shall see, NAT can also be synergistically combined with firewalls to produce combination devices that have become the most popular types of routers used to connect end users, including home networks and small enterprises, to the internet. We shall now explore both firewalls and NATs in further detail. Firewalls. Given the enormous management problems associated with trying to keep end system software up to date and bug-free, the focus of resisting attacks expanded from securing end systems to restricting the internet traffic allowed to flow end systems by filtering out some traffic using firewalls. Today, firewalls are common and several different types have evolved. The two major types of firewalls commonly used include proxy firewalls and packet filtering firewalls. The main difference between them is the layer in the protocol stack at which they operate, and consequently, the way IP addresses and port numbers are used. The packet filtering firewall is an internet router that drops datagram that fail to meet specific criteria. The proxy firewall operates as a multi-home server host from the viewpoint of an internet client. That is, it is the endpoint of TCP and UDP transport associations. It does not typically route IP datagrams at the IP protocol layer. Packet filtering firewalls. Packet filtering firewalls access an internet routers and filter drop some traffic. They can generally be configured to discard or forward packets whose headers meet or fail to meet certain criteria, called filters. Simple filters include range comparisons on various parts of the network layer or transport layer headers. The most popular filters involve undesired IP addresses or options, types of ICMP messages, and various UDP or TCP services based on their port numbers contained in each packet. As we shall see, the simplest packet filtering firewalls are stateless, whereas the more sophisticated ones are stateful. Stateless packet filtering firewalls treat each datagram individually, whereas stateful firewalls are able associate packets with either previously observed packets or packets that arrive in the future to make inferences about datagrams or streams, either those belonging to a single transport association or those IP fragments that constitute an IP datagram. See Chapter 10. IP fragmentation can significantly complicate a firewall's job, and stateless packet filtering. Firewalls are easily confused by fragments. A typical packet filtering firewall is shown in Figure 7.1. Here, the firewall is an internet router with 3 network interfaces, an inside, an outside, and a third DMZ interface. The DMZ subnet provides access to an extranet or DMZ where servers are deployed for internet users to access. Network administrators install filters or access control lists, ACLs, basically policy lists indicating what type of packets to discard or forward in the firewall. Typically, these filters conservatively block traffic from the outside that may be harmful and liberally allow traffic to travel from inside to outside. So in Figure 7.1, we see a typical packet filtering firewall configuration. The firewall acts as an IP router between an inside and outside network, and sometimes a third DMZ or extranet network, allowing only certain traffic to pass through it. A common configuration allows all traffic to pass from inside to outside, but only a small subset of traffic to pass in the reverse direction. When a DMZ is used, only certain services are permitted to be accessed from the internet.